I'm going to move into chapter 2, and don't worry, we're actually going to go back to chapter 1 after we pick up some things from section 2.1. And you can see I'm not actually starting from the beginning. That's because personally, what I prefer is to have the more general definitions come first, and then see special cases of them come afterwards. So this is going to be a little bit backwards from how it's written. Okay, so don't worry, we will be going back to chapter 1 for a long time probably. All right, so here's our new definition. We've defined this concept of measurable space. So assume that these two are measurable spaces. That just means that you've got a set and a sigma algebra on that set. That's it. So just like a set with a metric is called a metric space, a set with a sigma algebra is called a measurable space. Now, if you have two measurable spaces, x and y, and a function from one to the other, then I'm going to define what it means to say that f is a measurable function. So we say f is a measurable function if and only if, for all measurable subsets of y, we have that the preimage is measurable. Okay, so if you think of the idea of being an element of a sigma algebra as being a measurable set, that's how the word measurable set is used. It means you're in the sigma algebra. If you think of it that way, then you can think of this condition as saying the preimage of a measurable set is measurable. So a measurable function is the one for which the preimage of a measurable set is always measurable. So this should remind you of something that we saw before when we were looking at metric spaces. So here I am in Rudin at the definition of continuous function. And I'm not going to look at the definition, but I'm going to look at something that's equivalent that could have been the definition. So we could have said that if f maps a metric space x to a metric space y, then we say that f is continuous if and only if the preimage of an open set is open. So this is the same thing basically, except that the word open is being replaced by the word measurable. So where continuous functions are ones that preserve openness in terms of preimage, measurable functions are ones that preserve measurability of sets in terms of preimage. And we might actually sometimes say that f is a AB measurable function rather than just saying measurable function, just to be more explicit. So if we need to explicitly specify what are the sigma algebras we're talking about on x and on y, then we can use this language. And I'll probably use this a lot. Okay, so I went and I gathered some of the terminology that we have defined or that we will define that somehow uses the word measure or derived terminology from the word measure. And this is what I found. There are a lot of different concepts that use this terminology that can easily be confused. So let me try to get things in order. So some of these we haven't really talked about yet, but I just want to show you that they're there. For example, a measurable space is different from a measure space. A measurable space is different from a measurable set. So these we've defined. Measurable space is a set with a sigma algebra. So as long as this is a sigma algebra on X, then this pair together would be called a measurable space. A measurable set would be like if you have something in a sigma algebra. So think of the sigma algebra as like fancy A, the collection of subsets of X, and then a specific measurable set would be a non-fancy capital A, a particular subset of X which is in the sigma algebra. And a measurable function is the kind of thing we just defined where, it's from one measurable space to another. So each of these is a measurable space. A measure, well, we haven't defined measure yet formally, but we've seen an example of something that acts like it at least, or that might be a candidate for one, which is the Jordan measure. So that was a map from this collection of so-called Jordan measurable sets to the reals. Later we'll define precisely what is a measure. And a measure space will be a measurable space equipped with a measure. So there'll be more to that. Okay, but we haven't done these. So far we've done these three. Okay, so hopefully this helps you keep track of the language that's being used. Sometimes, people will just use the adjective. So often I'll just take a function and I'll be like, hey, this function is measurable, or it's not measurable. Then you know that I'm talking about this idea of measurability for a function. Another thing about this definition, before I move on from it, the definition of measurable function. So if you look at what it's saying, to say f is a measurable function is to say that the preimage of any b in script b is in script a, right? Well, we have a name for the collection of preimages of all the b's in script b. It's what I was referring to as the pullback of script b along f. So in other words, another way to express this definition is if you take the pullback of script b along f, well then you'll get some sigma algebra on x, right? And what this is saying is that everything in there, all the preimages of the b's here, they're all in script a. So that's what it's saying. So this actually gives you a nice way to think about what this pullback is. Although we explicitly said what it is, you can also think about it as the smallest possible sigma algebra on x that makes f a measurable function. Because you see, we're defining measurable function to mean that the pullback is of the sigma algebra on y is contained in the sigma algebra on x. So that means the sigma algebra on x has to be large enough to contain it. The smallest that it can be, the smallest that the sigma algebra A could be, while still keeping f as a measurable function, is for it to be this. Also, there's one special case of this definition which gets its own terminology sometimes, which is when the domain measurable space happens to be a metric space, and its sigma algebra happens to be the Borel sigma algebra. Then people say, for measurable function, they'll say f is Borel measurable, or they'll say it's a Borel function. So in the case where x is a metric space, I used to write ms for metric space, but now that could mean measurable space, right? In the case where x is a metric space and also a measurable space with a Borel with a Borel sigma algebra, in the case where x is a metric space, with this being the Borel sigma algebra on x, we would describe let's call it Borel sigma algebra on x, comma b measurable function as being Borel, as being a Borel function or a Borel measurable function. So that's terminology you will see used sometimes. We might use it sometimes. Personally, for now, I'm just going to prefer just saying outright what are the two sigma algebras involved in any statement about a function being measurable. So I'll probably just use this language.